go ahead and take a peek at Objective 4, calculating theoretical yield. In our first equation, it says aluminum oxide combines with water to form a base. This is coming from our combination helpful hint page. When I think about aluminum oxide, that's Al with a +3, O with a -2, so when I crisscross, we get Al2O3. Reacts with water. Since this is a combination pattern, I don't really need to write water as HOH. I just like writing water as HOH for those replacements. When a metal oxide combines with water, we have a helpful hint. Metal oxide with water looks like helpful hint number 4. I'm seeing it hanging from the ceiling there. Number 4, to make a base. A base says take your metal, aluminum, who's a +3. A base ion is the hydroxide, the polyatomic OH carrying a -1. So when we crisscross, we get AlOH taken 3 times. Helpful hint number 4. Metal oxide and water makes a base. It just hooks by charge. Let's see, we've got 2 aluminum on the left. I bet we'll need a 2 out front of the product. That gives us 6 H's and 6 O's. Putting a 3 in front of the water gives us 6 H's, and 3 plus 3 is 6 O's. Al2O3 with 3 waters combines to form 2 units of aluminum hydroxide. In an experiment, we have 930 grams of our reactant, aluminum oxide, Al2O3. It was reacted with excess amount of water. If we produce 1.35 kilograms of our base, aluminum hydroxide, what is our percent yield? Since I'm given a gram unit and a kilogram unit, I'm also just going to take a moment to flip that unit out. 1350 grams is the same number as 1.35 kilograms, and now I have 2 like units to compare. This is what we call our actual yield, and since we didn't run the experiment, that has to be provided. If we ran this experiment and we produced 1350 grams, that would be called the actual yield. Some people call it experimental. We need to do our 3-step stoichiometry problem to solve for our theoretical yield so we can compare the two, knowing that our target is our base, AlOH taken 3 times. Given a mass, we'll calculate a mass, where the target now will be called our theoretical yield of our base. We know in our first conversion factor of Al2O3, we'll need a molar mass to convert grams to moles. Aluminum, who has a molar mass of 27, there's 2 of those. Oxygen's molar mass is 16, there's 3 of those. I hit that out for us, it was 102 grams for Al2O3. Here's the ratio of want over given, the heart of a stoichiometric value. We want 2 moles of our base, AlOH3. Starting from that first reactant, 1 mole of Al2O3. So the want over given ratio is 2 over 1. We know in the last conversion, we'll need a molar mass of our product. Aluminum is 27. We've got 16 times 3 for the oxygen and 3 more for the hydrogen. I get 78 grams for the molar mass of our base, aluminum hydroxide, in every 1 mole. Every number has a number unit label. We can see how they'll cancel. Let me hit for us. 930 divided by 102 times 2 times 78. And I get 1422.4 grams of aluminum hydroxide. That would be ideal if everything worked perfectly. Going back up, it says we made 1350 grams as our actual yield. Our target was 1422, and I'll express that as a percent to find the efficiency of our reaction. So 1350 in a gram unit divided by 1422.4, the answer to the stoichiometry problem expressed as a percent. This has a 94.9% yield, not too bad. Let me pause here. Now that you've seen one, I'm going to give you a little moment of music. Try the next one, and we'll come back and share some answers.